This is the 7th section of the number theory chapter, and this is on combinatorics. Now this is all about combinations and permutations. So we're going to run through the rules. So this intro might be slightly longer than normal, but then it does mean when we get to the questions we'll be able to get through them quite quickly. So for each one I will give you the rule and then we'll do an example. So let's say, for example, I'm going to a shop, they've got a meal deal, and let's say, there are 5 different choices of sandwiches, 3 different choices for crisps, and 7 choices for drink. And I want to know all the different combinations there are possible for sandwich, crisp, and drink. Well, I would multiply those numbers together. So I'll just do 5 times 3 times 7. And that gives me my first rule. Now, each one of these n's here is going to represent the number of choices there are available for each item. So here we have item number 1. How many choices do we have? So this might represent 5 different types of sandwiches. N2, so this will be the number of choices for the second item. And then we can carry on the number of choices for the third item. Now, let's say we have up to k items. This calculation will give us the number of combinations of k items where each item has n k choices. So here's an example. So meal deal consists of sandwich, crisps, and drinks. So let's say there are sandwiches, I think I'll spell that right, and crisps and drink. So let's say I've got 5 different choices for sandwich, 3 choices for crisps, 7 choices for drink. So the total number of combinations is just going to be 5 times 3 times 7. So that tells me that there are 105 ways or combinations for sandwich, crisps, and drink. So N1 in this case represented the number of choices for sandwich, 5, N2 the number of choices for crisps, and the number of choices for drink. So it's just multiplying them together. So that's our first rule. Now our second rule is to do with sets. Now we can define a set. So let's say I've got a set S that has some items in it, and these items here, these are going to be numbers. So let's say I've got a set that contains n items, and I want to pick subsets from that item. Okay, so I want to pick subsets. Now what is a subset? A subset is basically a set that contains some of these items. So a subset could contain 1 item, 2 items, 3 items. It could actually contain no items. And if we have a subset that has no items, it's known as the empty set. And even that is a subset. So the empty set, which will basically just look like this. Okay, there's nothing in it, just 2 curly brackets. And this is the symbol that we have for the empty set. The empty set is a subset of S. In my case, I've defined S up here. Now the rule is that the number of subsets is equal to 2 to the power of n, where n is the number of items in the set. So I'll just put that down. So n is number of items in the set. So here's an example of that type of question. So let's say I had a set like this, and my set contains the numbers 3, 4, 5 and 6, and I want to find all the subsets of it. Now that would actually be 2 to the power of, well, there are 4 items in the set, so 2 to the power of 4, 16. But I'm actually going to write those items down so that you can see it's actually 16. So I've started off here with the empty set that contains none of the items, and then sets here that contain 1 item. Next, these are the sets which contain 2 items. I apologize for my curly brackets. I'm not very good at doing them. That's followed by these 3 subsets here that contain 3 items. And lastly, these are the sets that contain, well, there's one set that contains all of the items. So that tells you actually the set is a subset of itself. So this, the whole set is a subset. So I'll just put that down here. So the whole set is also a subset, just like the empty set here is also a subset. Now if I count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which means I must be missing one out. And yes, there was one more set that contained the items 4, 5, 6. I missed that one out. So there we go. There's all 16. Now you can see by listing I actually missed one out, and we wouldn't try and find the number of subsets by listing because it will just take too long. Imagine 10 items in our set and we do 2 to the power 10. We're not going to do it. So we will use this rule here. So the number of items in the set, 2 to the power of that, will give you the total number of subsets. Now watch out for questions where maybe you don't include the empty set, or you may not include the whole set. So watch out for questions like that, because you may need to remove these sets from the final answer, so your answer might be like 15 or 14. Right, let's clear this off and we'll look at the next rule after this. So I'll just get rid of this. And this is all about the number of ways or permutations, and you'll understand what we mean in a moment when we do an example, of n items. Okay, now permutations is different to combinations, because permutations means that you can accept items in a different order. So for example, if I look at this subset here, 3, 4, in permutations, I would actually accept 4, 3, because that's a different order. Okay, so let's go through the rule here. So the number of ways, and proper name for that is permutations. Of ordering n items is n factorial. So in this example, let's say that we've got 3 items. So I want to find the number of permutations of these 3 numbers, 1, 2 and 3. In other words, how many different ways can I write 1, 2 and 3? What's all the different orders? Sometimes this question appears something like this. Basically the number of different numbers you can make, number of different numbers you can make with like a certain set of digits. So let's say you've got the digits 4, 5, 6, 7. How many different numbers can you generate using those numbers 4, 5, 6, 7? That gives you the number of permutations. So using the rule, it would be 3 factorial for this question here, because I've got 3 items. So 3 factorial, that's just 1 times 2 times 3, which is 6. So I'm going to actually list them so you can see. So if I listed all the different permutations of 1, 2, 3, so I can write it as 1, 2, 3, 1, 3, 2. That's a different permutation, a different ordering. 2, 1, 3, 2, 3, 1. I'm trying to be systematic in the way that I list them. 3, 1, 2, and lastly 3, 2, 1. So I can see here 1, 2, 3, 4, 5, 6. So I've got that list right. So 3 items, and these are all the different permutations. Now notice that's different to what we had over here. So when I had a subset of 3, 4, 5, the subset of 3, 5, 4, I count as the same thing. If the same items are there but in a different order, it counts as the same. Whereas with permutations, the order doesn't matter. This will come up a bit later as we go on to some other rules as well. Right, so let's clear this and we'll move on to the next rule. Okay, so this rule is that the number of permutations, so we know what permutations are now, where the order doesn't matter, of R items taken from a set of n items is equal to this, n factorial over n minus r factorial. Now there's actually a button that will work this out for you, and it's called NPR. Now you may have come across NCR, which we'll be looking at in a moment. C stands for choose, P stands for permutations. So we can either work this value out manually, or we can use this NPR button on our calculator. Now to access it on your calculator, you'll need to type in the value of n first. Then you'll do shift and the times button. So shift followed by the times button. It's above the times button, and then you'll type in your value of r and then equals to give you that value. Okay, so here's an example. Let's say I want to know the number of permutations let's spell it right, permutations, that wouldn't be right, would it? Permutations of 3 items taken from 10 items. Now this question may be worded slightly differently. It may, instead of the word permutations, it may say the number of ways of ordering 3 items taken from a set of 10. So the wording may be slightly different. Now I'm not going to list all of them. I'll start the list off because the list would be very long if I carried on. So for example, if these 10 items were just the numbers 1 to 10, then I could pick 3 items. I could pick 1, 2, 3 from that list. A different way of ordering the 3 items would be 1, 3, 2, and then 2, 1, 3, for example. I can keep going on my list, and then I might get to 7, 8, 9 at some point, and then 7, 9, 8. So can you see that, you know, we can do things in different orders? That counts as a permutation. And then towards the end of my list, I'm probably going to have something like 8, 10, 9, and then 8, 9, 10. Now, if I was to do all of these, I would have quite a long list. So if I use either NPR, my calculator, so I've got 10 items, and I'm picking 3 from that list. If I work that out on my calculator, I get 720. If I use the manual way of working it out, I'll also get 720. In this case, n would be 10, so I would do 10 factorial divided by 10 minus 3 factorial. So basically, it'll be 10 factorial divided by 7 factorial. And that also gives us 720. So this is the number of permutations, or the number of ways of ordering a certain number of items, or a subset of a certain item of items taken from a whole set of n items. Now for the next rule, looking at this last rule that we've got here, in the example that I gave, every item in the set that I was choosing from n was different. But we can get items in a set here which are duplicates, the same item occurring 2 or 3 times, or even more than that, like in words. Yeah, you get certain words where you've got identical letters there, and that's going to change our rule slightly if we want to work out the number of permutations of the letters in that word if we've got some repetition of letters. So if any of the items are identical, so this, like what you get in words where letters come up more than once, then the number of permutations now becomes this. So n factorial, so n is like the total number of items, including the repeated ones, divided by this. Now I'll explain this in a moment. So r1 factorial times by r2 factorial times by, I'll just put ... up to I'll just put rk factorial here. Okay. So as you said, the n up the top represents the number of items. So that might be, for example, the number of letters in the word. So number of letters in the word. But these ones represent, each R represents the number of repetitions of a single letter. So let's say we had a word that had 2 E's in it, we would put 2 factorial in here. So if there was just one letter appeared twice, then we'd put 2 factorial, we don't need the rest. But let's say in the same word, the letter C occurred 3 times. So then we'd put 3 factorial. So each one of these R's represents like the letter that's repeated, and R is the number of times that letter is repeated. So I'll put R equals the number of times a single letter is repeated. Now if you have second letter repeated, then you'd multiply by that. If you had a third letter repeated, okay, up to R to the K, where this will be the kth letter that's repeated. So I'll just put that down, kth letter that is repeated it'd be R times, wouldn't it? R times. Okay, so let's do an example. So let's say I wanted to know the number of permutations of the letters in the word wheel. So there are 5 letters in the word, so that'll be n will be 5, so 5 factorial. And one of the letters appears twice, so I need to divide it by 2 factorial. So that would give 60 permutations. There'll be 60 different ways of ordering these letters in the word wheel. Now, just for the sake of it, because I can't think of a word that with letters that come up twice. So let's say we've got the word wheels, okay, like that, with 4 S's on the end. So for this, the working is going to change slightly. So now I've got a word that has 10 letters in it, where the E occurs twice and the S appears 4 times. So it'll be 10 factorial divided by 2 factorial, because the E occurs twice, times by 4 factorial. Now it should be 5 factorial. There are 5 S's there. So very long word, made up word. And that gives, well, actually gives 15,120 permutations. So that's why we don't do these things by listing. So we're now on to the last rule, which is where we want to find out the number of ways of picking R items from N items. Now I'm actually going to change the the number of ways of not picking, but choosing. So it just goes with the name of the rule. So the number of ways of choosing R items from N items is given as NCR. Now this can be written in different ways. You'll often see it written as N over R. This can be worked out manually as N factorial over N minus R factorial. Okay, so that bit's the same as the permutations formula, but then we times by R factorial. So you can use your calculator to work this out, and it's actually shift and divide to get this button. So you would type in first of all your value of N, then you would do the shift button followed by divide, then you type in your value for R and then equals, and it will give you a value. Now this is different to NPR because with NCR, different orderings of the same items count as the same thing. I'll write that down. So with NCR, different orderings of the same item, count as the same ways of choosing. So for example, if I had 10 items and I picked 3 items from there, and I picked 1, 2 and 3, okay, unlike permutations, I can't have 1, 3, 2 or 2, 1, 3 or any permutation of the same 3 items. So with NCR, we are only allowed 1. We're picking 3. We're picking 3 items. A permutation of that does not count. Now, you would have come across NCR with binomial, when you work out the binomial distribution, and yeah, you're working out then a number of ways of picking R items from N. Okay, so here's my example. Let's say I've got 5 sweets in a bowl, so each one of these represents a sweet, and I'm allowed to pick 2 sweets from these 5, and I want to work out what's the number of ways of choosing 2 sweets from this 5. Now, if I pick sweet number 1 and sweet number 2, that will be the same as picking sweet number 2 and then sweet number 1. So with this choose NCR, choosing sweet 1 and 2 counts as being exactly the same as sweet 2 and 1, which wouldn't be the same with permutations. So if I want to find the number of ways, so we need to pretend these are sweets here, number of ways of choosing 2 sweets out of these 5, that would be 5C2, which you could also write as 5,2 like this. We could work it out manually by doing 5 factorial over 5 minus 2 factorial times by 2 factorial, or you can just use the NCR button, that would be quicker. So I'm going to do that now. So it'll be 5 shift divide 2. So that gives me 10. So there would be 10 ways of choosing 2 of these sweets from the 5 that are there. Okay, so in this example, we've got a number plate on a car that consists of 2 letters followed by 2 digits followed by 3 more letters. So here's an example of what that number plate might look like. 2 letters, 2 digits followed by 3 more letters. The letters can be chosen from the entire alphabet except the letters I, Q, and Z. I suppose that's because I looks like 1, Q from a distance might look like 0, and Z might look like 2. And the digits can be chosen from 0 to 9. So in part A, what we need to do is to find a total number of different number plates that can be generated in this way. So this is the type of question where we have different items, and each item has a different number of ways of choosing that item. So this is the calculation that we would do. This is the formula that we would use for that. Right, so let's start with the first letter here. Well, the alphabet contains 6 letters, but we can't use 3 of them. So there are 26 different choices for the first letter. Sorry, not 26, 23. Okay, the same for the second letter. There are 23 choices, so we times by 23. Then we get to the numbers here. So the numbers can be from 0 to 9. So be careful, that's 10 choices, not 9, because that includes 0. So times by 10. Then the next digit, we've got 10 choices. And then for each of the last 3 letters, we have 23 choices. Now, let's multiply these together and see what we get. So it's basically 23 to the power 5 times by 100, or 10 squared, I suppose. So that gives lots of choices. Now, 643, so I think it's 643 million, 634,300. So over about, well, nearly 6.5 million choices. Okay, part B. Now part B says that all the number plates generated in one particular region must start with the letters combinations C, W, or CX. We want to find the total number of different ways number plates can be generated in this way. Now this changes the first part of the number plate. Instead of having 23 choices for this and 23 choices for this, for the whole first section of the number plate, we only have 2 choices. So actually, all of this just becomes one calculation which is 2. I suppose you could instead say, right, we've only got one choice for the first letter, C, times by 2 choices for the second letter, 1 times by 2, but we can just put 2. There's only 2 choices for that. The rest of the calculation remains the same. So we've still got 10 choices for the 2 numbers in the middle of the number plate, and then we've still got 23 times 23 times 23 choices for the last 3 letters. So let's work that out. So the first bit's a bit like 200, 2 times 10 times 10, times that by 23 cubed, and we get just over 2 million, I think. So this is 2,433,400 different number plates. So I'll just put different number plates, different number plates. Right, so here we want to find the total number of 3-digit even numbers. Okay, a little diagram here might help. So here's my 3-digit even number. Now if it's a 3-digit even number, this first digit can't be 0. So can't be 0. So that leaves basically 1 to 9. So that leaves me 9 choices for the first digit. The second digit can be can include 0, so there's 10 choices for the second digit. Now if it's an even number and the third digit needs to be even, well, or the number needs to be even, it can only be 0, 2, 4, 6, 8. So there are 5 choices for the last digit. So the total number of choices is just going to be 9, or total number of 3-digit even numbers, 9 times 10 times 5. So that's 90 times by 5. So there are 450 3-digit even numbers. 3-digit even numbers. So here we want to find the total number of positive integers less than 1,000 that contain the digit 5, and in part A is exactly once. So let's consider the different positions where this digit could be. So the 5 could be here. Now if it's only going to appear exactly once, we can't have a 5 here. We can have all the other digits but not 5 there, and we can't have 5 here. So if the 5 is going to be in the first position, that's only one choice. If we look at the second digit, then because it can't be a 5, that only leaves 9 choices for the second digit, basically 0, 1, 2, 3, 4, 6, 7, 8, 9. And then the same for the last digit. So the last digit can be any digit but not a 5, so it only leaves 9 choices. So if the 5 is in the first position and no other 5s anywhere else in the number, then we've got 81 choices. Okay, now let's look at if the 5 were in the second position of the number. So let's say the 5 was here. So this can't be a 5, so not 5. This can't be a 5 either, not 5. But because I'm now considering 2-digit numbers, here it was like and the 2-digit numbers as well. So I've got 9 choices for the first digit, 1 for the second, 9 for the third digit. So this first digit here could be a 0. That means that it then includes the 2-digit numbers as well. So this is also 81 choices. You might be seeing the pattern here. If I now consider the 5 to be in the last position, like this, so these can't be 5. Now they can be 0s, so that I include the 2-digit numbers and 1-digit number. And again, this leaves 9 choices for the first digit, 9 for the second, 1 for the third, gives 81. So the total number of positive integers where there's only one 5 is 243. There are other ways of doing it, but I've just considered basically where the 5 could be in the first position, the second position, or the third position. And these leading digits, the digits at the front of the number, can be zeros because I want to make sure that I include 2-digit numbers, so where that would be 0, and 1-digit numbers where both of these would be 0. Right, now part B, I want to find the total number of positive integers less than 1,000 where the 5 occurs at least once. Now I've done some of the working already. So if it occurs at least once, that means that the 5s could occur either once, twice, or 3 times, thrice. Now once we already know, we've worked that out already, that's 243. So we just need to work out what these other values are, and then we'll add those on and work out the total. Now this one we don't need to work anything out. If there's going to be 3 5s in a number, there's only one of those, so that's going to be 1. So we only need to work out this twice here, the number of ways we can have with 2 5s in a number. So let's do it like this. So we've got our 3-digit number there, so the 5 could be the first 2 places there, and not a 5 in the last one. Or it could be that we have a 5 in the first and the last position, so a 5 here, a 5 here, not a 5 here. Or it could be that the 2 5s that we have appear in these 2 positions here, 5 and 5, not 5. Okay, so they're the only positions where we can have 5. So first 2, first and third, second and third. And we're going to work out how many different ways there are of doing this. So if we've got 5 in the first position, so there's only one way of doing that, one way of doing this. The last one, well, we have 9 ways of doing that. It can be any digit but not a 5, so that's 9. So that gives us 9 ways of getting numbers like that. The second one, we will have 1 way of doing this. Now the second digit can be any digit but not 5, so there's 9 ways of doing that, and only 1 way of doing the 5 at the end. So that's going to be 9. Again, you might be seeing the pattern here. With this one, last one down here, we need to consider the fact that it could be a 2-digit number with a 5 here and a 5 here. So that would be 9 ways of doing this, not 8, because we can include 0, 1 and 1, and notice it's 9 again. So what do we have? We have 27 ways where the number occurs twice. So all we need to do is to add those up and we get our answer. So we've got 243 plus 27 plus 1. So 243 plus 27 plus 1, and I get 271. 271. Now there are other ways of doing this, but basically we've got 271 ways. So there's answer for B, and there's our answer for A. Okay, so this question is about finding a number of subsets of S. Now remember, the way to find the number of subsets is 2 to the power n, where n is the number of elements in the set. So number of subsets, this includes the set, which is all of the elements, and the empty set is 2 to the power n, where n is the number of elements in the set, number of elements in the set, and in this case is S. So all we need to do is 2 to the power, and we've got 6 elements, 2 to the power 6 which is 2 to the power 6, is 64. So there are 64 subsets of this set here. Okay, a group of 10 students are being selected to clean up a local park. Good. Don't want them leaving it in a mess. Given that at least one student must be selected, so at least one student needs to be selected, so we can't have no students selected. How many different groups of students could be selected to clean up the park? So this question is about subsets. Yeah, subsets where we've got a choice of 10, or basically a set of 10. And we want to find all the subsets. So we want all the subsets except the empty set, because we need to have at least one student. So except the empty set. So if there are 10 elements or students in this set, so number of sets is going to be 2 to the power 10, but I'm going to subtract 1 because I don't want the empty set. Okay, so I don't want this empty set. So 2 to the power of 10 is 1024. Take away the 1, so that leaves 1023. So there's lots of ways of choosing at least one student to help clean up this park. Okay, so we've got these 6 items here, the letters A, B, C, D, E, F. Find a number of different strings of length 6 that can be written using these letters exactly only once. So this part A involves n factorial, because we want basically the number of ways of writing out these 6 letters in any order. And that's just going to be n factorial. So n is 6. So we work out 6 factorial, which I believe off the top of my head, because you work it out quite often, is 720. 1 times 2 times 3 times 4 times 5 times 6. Part B says find a number of these strings that contain the subset D, E, F. Now what I'll do, I'll write out the letters like this: A, B, C, D, E, F. And it says it must contain the subset D, E, F. So imagine if you clump those together as one. So now we can think of this as a set containing 4 items or 4 elements. Yeah, because a D, E, F, that's going to appear anyway. So in the first part of this question, we could think of this as being 4 items. So we just work out 4 factorial, which is 1 times 2 times 3 times 4 is going to be 24. Yeah, so this subset must appear. So we can group it together and think of it as a single item. And then in the second part of part B, it says the letters D, E, and F together in any order. So in this part of the question, the D, E, and F don't have to be in that order. They can be in a different order. So let's think about that, the D, E, F. So the number of different ways they can be written in any order will be 3 factorial, which is 6. So we can now think of this question like this: the A, B, and C, then this like other set of digits which must contain, which can occur 6 times. So this is very similar to the last one. In the last one, we just said, well, it's just it's got to be in that order. Since they can be in any order, there's now 6 different ways that we can write this. So now it becomes 4 factorial to 24 times by the 6 different ways we can write these last 3. So that's going to be 4 factorial times by the 3 factorial which is 6. So that's going to be 24 times 6, which is, let's use my calculator, 24 times 6, 144. So that will be my answer to part B, 144, and well, the first part of part B was 24 and then A was 720. Okay, so here we've got 15 runners that complete in a cross-country race. Find the number of ways the top 6 positions can be filled. Now this is a permutations question. So this is the formula that we would use. Now the reason it's a permutation question is that we've got a choice of 15 runners and we're picking 6 from those 15. But those 6 could be in any order. So it could be that the top six positions are 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 6, 5. So we've got all these different choices, these different permutations. So this is the formula that we need to use. So in this case, when we use the formula, n is going to be 15, because there's 15 runners to choose from, and we're choosing 6 of those. So we need to do 15 P6. Now we can use our calculator to do that, or if we work it out manually, that will be 15 factorial over 15 minus 6 factorial, in other words 9 factorial. So I'll use the P button, so I'll just type in 15, shift and times, and then 6, and I will get, it's up 3,603,600. There we go. Okay, so on this one here it says find a number of possible permutations of the letters in the word winnings. Now here we have repetition. Okay, we've got 3 N's and we've got 2 I's. When we want to find a number of permutations and we have repetition, this is the formula that we use. N factorial divided by the number of times each one of these repetitions occurs. Okay, so here N would be how many letters we got? 1, 2, 3, 4, 5, 6, 7, 8 letters. So N is 8. R1. Now if I think about the I, that is repeated twice. I'll just put I repeated twice. And then R2, that would be 3, because the N is repeated 3 times. Repeated times by 3. So if I plonk that into my formula, I will have 8 factorial divided by 2 factorial times 3 factorial. So we will work that out. 8 factorial is 40,320, and I divide that by 2 factorial, which is 2, times by 3 factorial, which is 6. I divide it by 18 and I get 3,360. 3,360 for this question. Okay, so in a lottery game, you choose 6 numbers from a choice of 45 by shading in a grid. So I'm guessing like that's N is going to be 45 and we're choosing 6, so that's like my R. 6 numbers are selected at random, and if you match all 6 you win a prize. So if you match all 6 you win a prize, or you win a jackpot prize. Find the probability of winning a jackpot prize. Now if you match 6, the order that you get the 6 doesn't matter. So if the winning numbers were 1, 2, 3, 4, 5, 6, if you picked 1, 2, 3, 4, 6, 5, it counts as the same. So this is not permutations. This is choosing 6 from 45. So this is NCR for this question. So N is 45, as we said. Don't need to write it down again, I suppose I will do. R equals 6. So we want 45, choose 6. Now remember, that could be written as 45, 6, like this. We're going to use our calculator to work it out. But if you're working out manually, that would be n factorial over n minus r factorial. So this bit looks like the permutations bit. Then we add dividing by the r factorial as well. So that will be 45 factorial divided by 45 minus 6 factorial times by 6 factorial. So that gives 145,145,060, but we need to give the probability of winning. So the probability is going to be 1 over that number. There we go. Okay, so in a poker deck, a deck of 52 cards is used. It's underlined 52 cards. There are 13 cards in each of 4 suits. So that's hearts, diamonds, etc. If you know about cards, that type of thing. I don't think that's really important in the question. A hand is made up of 5 cards arranged in any order. So when you see that any order, that tells you NCR. If it says they need to be in a specific order and what are the permutations of those orders, then we'd use NPR. But because they can be in any order, then it's NCR. Work out the total number of different hands that are possible, right? So we have n equals 52 because we're choosing from 52, and the items we're choosing from 52 is 5. So we need to work out 52 C5, which can be written as 52 5. We'll use our calculator, but we'll write down what it is if we're working out manually. So 52 factorial divided by 52 minus 5 factorial times by 5 factorial. Right, so 52 C5 is going to be 52 shift divide 5, and we get, it's another million, I think. Is it 25 million? No, 2,598,960. So there is that many number of hands possible. Right, let's move on to part B. A flush is a hand that containing 5 cards of the same suit. Okay, and there's 13 cards in a suit. Work out the number of hands containing 5 cards of the same suit. Right, so the first thing is, if these cards are all of the same suit, then we're only looking at 13 cards. We're not looking at the whole pack. So n is 13, and R is going to be 5 cards picked out of those 13 that are of the same suit. So this is 13 C5, which is 13 5, like this in brackets, which would be 13 factorial over 13 minus 5 factorial times by 5 factorial. So 13 C5, so 13 shift divide 5, and we're going to get 1,287. So this is for one suit. Okay, but there are 4 suits, so they could all be hearts, and we're picking 5 out of 13. They could all be diamonds, they could all be clubs, they could all be spades. So we need to take this and we need to times it by 4 because there are 4 suits. So timesing that by 4, we get 5,148 possible hands. So part C here, it now says 4 of a kind is a hand containing 4 cards of the same value, such as 4 sevens or 4 queens, but all 4 cards, they're all the same value. Work out the number of 4 of a kind hands. Okay, so in this part C of the question, what we need to remember is that we're picking 5 cards, yeah, and we want 4 of them to be the same. So we're still picking 5 cards. Now, there are 13 ways of getting 4 cards the same, yeah, because there are 13 cards in the suit. So they could be all ones or all twos or so on, all the way up to all kings. Yeah. So because there are 13 cards in a suit, there are 13 ways of getting 4 of a kind, 4 cards the same. But because we are picking 5 cards, once we've picked our 4 cards, the 5th card could be any one of the 48 that's left. So 52 minus 4. So this is where we use this multiplying rule to work out the total number of choices. You probably have to sort of think about this a couple of times before this part of the question sort of makes sense, because out of all of them, this is the hardest one really to get your head around. Yeah, so 13 ways of getting 4 cards all the same, but because we are picking 5 cards, the 5th card could be any card out of the 4 that are left. Now, don't assume that these are all the same and then the 5th one is different. This could take place in any order. So it could be that the first and the second one are the same, the third one is different, and then the 4th and 5th one are the same. That would be 4 of a kind, but the order doesn't matter. That's why we don't need to consider all of the other combinations. So if we do 48 times by 13 times by 48, we're going to get 624 ways for this one. So let's just highlight the answers before we move on. So that's part A, part B, and there we go, part C. Right, so this last question here. The set S contains these 8 elements here, and in part A what we want to do is to find the number of subsets of S containing exactly 4 elements. Now the order of those 8 elements doesn't matter. The word permutations isn't mentioned. So here N is 8, R is 4, and this is the number of ways of choosing 4 elements from 8. So it's 8C4, which we can write as this. If we were doing it manually, it'd be 8 factorial over 8 minus 4 factorial times by 4 factorial. But we will use our calculator to do it. We're not going to do it manually. And that would be 70. And in part B, it says the number of different 4-digit numbers that can be made using the elements of S. Each element can only be used once. Now, whenever you get a question that says the number of 4-digit numbers or the number of different numbers that you can make, this is permutations. So this is the number of permutations of 4 out of these 8 digits that we have. And because we don't have 0 here, we don't need to worry about whether it's got 0 at the front. So this is fine. We don't need to do any other work than that. So if we were working out manually, it would be 8 factorial over 4 factorial. But we'll use our calculator. So 8 shift times 4, and we get 1,680. So just highlight those answers there. You should now be able to do exercise 1G on pages 35 to 37. Now the recap is going to be quite lengthy, so rather than going through each of the topics, what I will do is list them now, and probably might want to pause them and have a look at them, or just go through the beginning of the video again. So here we go. These are all the rules that we've gone through in this section of this chapter.